case study today on unlocking the future of healthcare with ML and AI. So we have Huang, the Senior Manager of Health Data Science Branch with the Digital Analytics Strategy Division with the Ontario Ministry of Health. We have Sahar Asgari and Peter Hamilton, all joining us with the Ontario Ministry of Health.
It's worth it. We have a real treat for you. My name is Ching, Huang. I am the Senior Manager for the Health Data Science Branch of the Ontario Ministry of Health. And on stage with me today are two of our very talented technical members, Sahar Asgari, and she is the Senior Data Scientist. And we also have Peter Hamilton, who is a lead visual analytics developer. So today, our session is going to be interactive, but just a little bit about our team. We're a small, mighty team within the Ontario Ministry of Health. The ministry manages a $60 billion annual budget, serving over 14 million Ontarians, and our team, about 20 people, we run about 10 million. So, we operate on a shoestring budget, but we're able to do some really impressive work. At our core, we're all about model-driven analytics, and we're all about turning data into insights and insights into strategy, and you will see that showcased today in terms of the breadth and the depth of our work. So this is the same summary that is shown in the agenda. We have 3 demos for you. Sahar is going to walk you through the first one in terms of looking at climate change and healthcare resource. Peter is going to walk you through the second one, looking at working with non-traditional data types such as images. And I will walk you through the last one, looking at simulations and as applied to a policy question. So to kick you off, I'm actually going to hand it over to Sahar.
Thank you, Qing. This one, okay.
Yeah.
Emergency departments across Ontario are under a lot of pressure, and climate change is a key contributor to that pressure. We already know that emergency departments are dealing with overcrowding. Now, let's imagine how it would be when we have extreme weather conditions, such as heat waves, wildfires, or storm. Our goal is to develop a predictive tool to forecast emergency department visits related to climate. Why is this important? Because timely prediction gives us the ability to act before any crisis hits. This approach moves us from reactive to proactive, so we can help frontline providers, protect patients, and ultimately save lives. To achieve this goal, we need to use data sets from 3 key sources. The first one is using emergency department visits dataset from NACERS, or National Ambulatory Care Reporting System. And then combine this data with air pollutants and weather data, scraping from websites, which are publicly available, and use this data to test for machine learning models, including linear regression, polynomial regression, random forest, and XGBoost. Random forest gave us the best performance among these models. And we used random forest to identify top 5 features that gave us that affected ED visits strongly. And you can see those top features that we used in our machine learning models. Now, with this explanation, let's move on and take a look at the dashboard developed in Streamlit open source Python library by Health Data Science Branch team in Ministry of Health. The dashboard is organized into 3 main tabs: Note, Results, and Advanced Settings. Is it, okay, the video is playing. You can see the dashboard here. In the Note tab provides a brief description of how the tool works and general guidance for the users. In the Results tab, users can interact with the dashboard by making a few key selections. They can select whether they want to predict ED visits 3 or 7 days from the reference date, and then select the reference date by making these options available on the tool. And finally, select the hospital that they are interested in, and after making all these selections, click on Predict ED Visits button, and then see the results. The location of the hospital is displayed at the bottom, and the results appear at the right-hand side of the dashboard. You can also see a plot and table showing the actual and predicted ED visits values, and the user has the option to maximize them for better view. In the Advanced Setting tab, user can see the variables, air pollutant, and weather data that we use to forecast ED visits. Now I'll hand it over to my colleague Peter to show you a cool animation on ED visits and air pollutants.
Thanks, Sahar. So go ahead. So as part of our exploration of this problem, we created an animation to show the difference between the air quality during the 2023 Ontario wildfires and the number of ED visits that were occurring in the province at that time. So you can see on the left-hand side, there's a map of the central part of Ontario with different emergency departments clustered by color using a k-means clustering algorithm. And then on the right, we're showing those ED visits across time in addition to the air quality within those specific regions. So you can see around June, it sort of peaks, and then it starts to go back to better air quality. Moving on to the next project. This was our first time doing any kind of image recognition in the branch, so this was new for us. And the project was requested by a branch of the government that does auditing of data. So what the problem was that they had a large data set of ultrasound images, approximately 30,000, that they wanted us to classify. So there was two types of images, or they told us there were. A lower resolution Doppler image, which is seen on the bottom there non-Doppler image, which is seen on the bottom, which is black and white. And then above that, a higher resolution Doppler image. So we needed to make a machine learning model to classify between Doppler and non-Doppler. Part of our interest in solving this problem was that we needed to make a solution that scaled and also something that we could run on-premise so that we didn't have any privacy concerns in terms of sending data out to the cloud. So the actual impact of the project, we were able to create several models that were able to run in-house on a laptop. And we could actually run the inference part of the model and get results in about 30 minutes, compared to hiring a consultant, which would cost about 4 weeks of time at a pretty high rate of pay. So then finally, we came up with a metric to actually give us confidence in our model so that we knew that if we were to manually review about 3,000 images, we would have a 95% confidence rate in our model. And if we increase the number of those images, we would have an even higher confidence in the model. So next up is the solution overview. So this is what we actually ended up doing. So there was 3 parts to this. The first part was exploring the data that we actually had. So we took all those images and we put them through a metadata filter. So just looking at the actual metadata of the images. And then next up, we created a continuity filter. And the reason for that was we wanted to ensure consistency across the images so that we knew that they would be exactly what we were expecting and that they would play nicely with our machine learning models. So in the next phase, we actually moved on to classifying them. So we took a 2-pronged approach. One being a deterministic model, so a rules-based approach, and then the other actually deploying a computer vision model. So we were able to find a lightweight computer vision model that we could use on our laptops that would do the job for us. And then once we had the results from both of our methods, we looked at them and checked for discrepancy amongst their results. And then finally, we validated using a Jupyter notebook. We had some custom HTML that we wrote to display all the images so that we could quickly check and make sure there was no issues. So first up, the metadata filter. So in terms of metadata, we looked at a bunch of different aspects of it, but the most important aspect was the actual dimensions of the images, so that being their width and height. Once we actually looked at all the dimensions, we realized that a whole bunch of these images weren't even in scope. Some of them were X-rays, some of them were administrative documents, just things that somehow slipped in there that weren't actually meant to be there. So we took all those out, and then we were left with 4 dimension sets. A key part of this exploration part was using Jupyter notebooks. That was just made it really quick to iterate on the problem, allowed us to inspect images very quickly, just made the whole process really smooth. Next up was the continuity filter. So you can see in this example image, there's a couple key features we looked at in the image. One being the Philips logo, and then the other being a timestamp. So we used an OCR, so that's like a computer vision model, to translate those pixels into actual strings, and then check those values against expected patterns and expected values. And then once we were able to do that, we knew that the images themselves would have consistent layout throughout the whole set. So for that, we used a pre-trained OCR model called Tesseract. And again, that's an open source model. So once we had all of our images filtered with the pre-filter, we moved on to the actual classification. So this was the first part. This was the rules-based deterministic classification. So we looked at the legends color bar, because that was the most consistent spot that would actually have color in it. And we extracted strips of pixels from there, and then we're able to put all that pixel data into a database, and then start clustering those pixels into clusters. So immediately after we did this, if anything was grayscale in terms of the color that we extracted, we knew that it was going to be classified as a not Doppler image. So we could immediately classify those as not Doppler. But then the rest of them, we clustered into about 30 different clusters. And then once we had those 30 clusters, it reduced the dimensions of the problem from 30,000 images down to 30 clusters. And then we manually could look at those clusters and quickly say whether or not they were Doppler or not Doppler. The results of this were really good. In our evaluations, it never failed. It was 100%. So we were quite happy. We performed this first, and then we moved on to the computer vision model. The part of the reason we wanted to do that was to have a solution that scaled, as we potentially were thinking that we could use this as part of the pipeline of intake for ultrasound images across the province. So for this, we used a model called VGG16. So that's a computer vision model. It's a deep CNN developed by a university in the UK. So we used this on the full image set, and we extracted all the features out of that image set. We were able to run this locally on our laptops, and then once we got those features, which the features you can think of it as you're sort of boiling down those images to their core salient points, so that you can now use them to perform quicker pattern recognition. So after we had that, we combined those features with a pre-labeled subset of our data that we had labeled by hand. And since we had already completed the first part, the deterministic classification, we had a really good idea of what was in our data. So we were able to make sure our data set for the deep learning model was quite balanced, and that it had a really diverse array of images. And so we used that, and the results, again, were quite good. There was just a minor discrepancy between this and the deterministic model. So then finally, the validation piece, we displayed the images in a Jupyter notebook using HTML. So this is a great feature about Jupyter, that you can actually just write some HTML and then you can quickly show images or whatever it is you're trying to do. And we were able to quickly validate, and we were quite happy with the results. So now I'm going to pass it over to Ching for the next spot.
Thank you very much, Peter. So for a third demo, let me just quickly set the stage. Hospital overcrowding is a big problem in Ontario. So one of the policy solutions that's been proposed and implemented are the transitional beds or reactivation centers, RCCs. I know Unity and UHN, you guys are very familiar with this. So then the question to us is like, well, how well does it work? Does it actually work? And so I will show you a simulation that we're going to play to test this policy impact. So here, Peter has very nicely put together a dashboard with different compartments. You can see the green is representing hospital beds, and then patients will start going into the hospital and filling these beds. And then after some number of days they stay in the hospital, they will leave. Now, if the hospital is over capacity, they will end up in the hallway or in what's inappropriate areas. So what we want to do is have some transitional beds and see how this absorbs the overcrowding. And at the bottom of this dashboard, you can see there's a nice plot. So we've chosen a community hospital using historical data to show this. You can see that the simulation is playing. And this is just a Qing theory model, nothing super fancy, but here we're giving it a facelift. You can see patients are coming in, they're filling the hospital beds. The shades represent how long they stay. So darker the shade, the longer the patients stay. So you can see they're coming in to the hospital beds, and you can see the plot at the bottom is also generating the graph, and this is all happening in real time. But because this is a beautiful simulation, we can speed it up and we can go very, very fast. So let's fill up those 128 hospital beds, and boom, you can see that the hospital is over capacity, and at the bottom, see the purple? That's the hallway medicine that's currently happening. That's when patient occupancy is over the number of hospital beds. So I'm just gonna let this play for a bit, and let's pause, and we say, okay, let's add 10 transitional beds. So you can quickly add that to the dashboard there and restart. You can see at the top there, those 10 beds are immediately filled by patients. And these are no longer acute patients. They're typically patients that are looking for long-term care, post-acute continuing care, et cetera. So they're staying for a while. You can see the graph, the orange. It's soaking up some of the hallway medicine patients, but it's not really solving the problem. So let's pause again, and let's add more transitional beds and see what happens. And we'll replay again. Boom, immediately all filled up. So this is a really cool tool, really cool visualization that allows someone without a data background to just pull different levers and inputs to quickly test the different scenarios. And the take-home message for this particular hospital is that maybe transitional beds isn't quite the long-term solution needed to solve hospital crowding, and that we need to look at the allocations of the transitional bed across the province. Okay, and that concludes our demos. So lastly, what I want to close with is sharing some of the tools and resources that we use. As mentioned by Peter, a lot of these are open source libraries that come from academia that are validated, that we can use, or enterprise-grade solutions that ensures data privacy, because we work within the public sector, within the healthcare sector. That's extremely important. And I also want to talk about, generally our formulas to success is really around, making sure all of our work is client-driven. So our internal stakeholders come to us with a problem, and we try to come up with the right solution to solve it for them. When we come up with solutions, we're very agile, and we use very little resources to do these kind of prototyping. And then the output, our focus, is really on making something that really pops, that really speaks for itself, as Peter and Sahar has demonstrated. So, in closing, Sahar's demonstration, it's all about climate change. It's about anticipating future needs and system changes, which is very applicable to other parts of the public sector. Peter's demonstration is really about accountability and efficiency to other domains that are really relevant within the public sector. And then the hallway medicine is a really cool demo of really evidence-based decision-making. So I'm going to conclude my presentation here, and I think we have a few minutes for questions.
Hey, thank you for the great presentation, and this is a really nice work. But I have some questions related to compute. Like, for example, I think you are analyzing images, and it needs a lot of processing power. So I just wanted to know how you managed hardware for this. Like, are you using dedicated GPUs? And I know you are using open source for privacy, but is there any other reason? Like, is it because of cost efficiency also? Because I think there are some enterprise level solutions too, or you needed more control. And third will be, what is your vision on scaling it? And if so, like, how will you do it with the open source models?
So to answer your first question, in terms of compute, we were just using models that we knew we could run locally. So for instance, the VGG16, we used that because we knew we could run it on our local GPUs. And then the reason we were doing that is partly because of privacy issues and also issues with procurement. It can be difficult to get the right resources in a timely way. Sometimes in government, things can move slowly, as you might know. So that was the reason for that. And sorry, what was your third question?
I think with open source, it's hard to scale things. Like, if you don't use enterprise level technology, then I think it's hard to scale, right? Like installing repositories and everything.
Yeah, I mean, I think it would just depend on what package you're using. We do use Docker a little bit to do some of the scaling, so for certain instances we would use that.
Thank you so much.
No problem.
But last question, if you could get a enterprise level solution, would you opt for it, or is it the open source only for you?
I mean, I don't know if there's any reason we would go for an enterprise solution, especially cost savings that you can get from open source. Enterprise can be quite expensive sometimes, so we've been trying to do things as cost efficient as possible.
Hi, thank you for the great demos. I have two questions. One is for the climate and impact on emergency department visits. Could you comment a little bit on who the intended end users are? Is it meant for citizens to think about if they have a non-acute problem when they should go to emergency? Or is it for hospitals to do sort of more resource planning?
So we got this request from chief of medical office health, and then we worked on it. So we create a dashboard so anyone in the hospital can use it. It's not for public because there are so many private data in it. So hospitals can use it to decide beforehand how many resources they are going to need in future in case of emergency happens in weather condition. Yeah, that's hospital that using this tool.
Okay, thank you so much. My follow-up is, how does the ministry work with, because there are a lot of hospitals in Ontario, how does the ministry work with other internal systems that different hospitals may have already built for this kind of resource planning? Do you look at that as well, trying to integrate these solutions?
Oh, that's a really good question. So I think what you're talking about is really collaboration and partnerships. The way that our team has worked so far is being responsive to needs at the provincial level, and then have the appropriate stakeholders communicate and talk about how they would like to use these tools. So if there are local tools that are built, that's absolutely fantastic. But if you think about smaller hospitals that do not have the resource to do that, then this would be something that we can give them to help them to plan, and also give the province kind of like the bird's eye view. However, whatever level they want to drill down, then they can do that. But definitely that collaboration dissemination piece is super important.
Hi, quick question here. So I saw in your optimization problem that it was a very single variable analysis around number of beds only. Have you tried the analysis with a more multivariate approach with other variables such as the category of symptoms they came in with, which might require a bed or not, or external factors like how many 24/7 clinics are available in that area for that hospital, which might help with overflow? So just curious if you've tried like 3 or 4 other variables as well to see how that impacts your optimization problem.
Those are all great suggestions. Again, we're taking the lead from our client. So when we designed this tool, they just really wanted to see, okay, can this work? So definitely what you're suggesting are like the future states. Thank you.
Okay. All right then. I think that might cover us then. So thanks so much. Let's thank our panelists today for their talk.